In this video, we present our paper, HiScene, Creating Hierarchical 3D Scenes with Isometric View Generation. HiScene aims to generate interactive 3D scenes by treating scenes as hierarchical structures of objects. Our method decouples complex scenes into multiple incomplete objects through hierarchical scene parsing, then regenerates complete objects using spatial aligned generation method, thereby preserving the scene's 3D layout and supporting the reintegration of regenerated objects back into the original scene. In the field of scene generation research, existing methods primarily fall into three categories: image and painting-based method, native scene generation method, and 3D layout-based method. However, these approaches generally face limitations and objects cannot be decoupled or over-reliance on predefined 3D layouts. In recent years, with the advancement of generative model, we have witnessed the ability to create realistic images through text prompt and reconstruct 3D objects from single images. This leads us to question: can we combine 2D image generation technique with 3D object generation method to construct complex disentangled scenes? To achieve this goal, we propose HiScene. HiScene aims to bridge the gap between object-level and scene-level generation while producing 3D scenes with compositional identities. The framework achieves its objectives through three main stages. In the hierarchical scene parsing stage, we first add fixed prefix isometric view of to text prompt, then utilize 2D generative models to create candidate images. Based on selected image, we initialize the scene through native 3D generative model. The initialized scene renders multi-view images from predetermined viewpoints, and obtains entity masks through 2D segmentation network. Next, we employ 3D GS semantic segmentation method to decompose the scene, resulting in incomplete objects. For each incomplete object, we render multi-view images centered on the object and randomly select one as a candidate image for regeneration. The image will use a vision language model to detect object occlusion. Once occlusion rate exceeds threshold, all modal completion will be applied. Given input image with occlusions and its visible mask, our goal is to recover a complete object image. This task is defined as all-modal completion. We treat the all-modal completion process as a temporal transition video effect. Unlike traditional image and painting, all-modal completion requires the input of visible region masks for the occluded objects. Here we show an example of constructing dataset. Given an input image and whole mask, we randomly select another image to paste on the input image, thereby obtaining occlusion image and visible region mask. We employ linear blending techniques to transform the construction process into video data. To further address the shadow issues caused by occluding objects, we cannot collect enough data in real world. We utilize Objaverse dataset to construct synthetic data with shadow effects. After object normalization, to ensure objects are correctly placed on predefined planes, we apply rigid body simulation in Blender to simulate the natural falling process under gravity, thereby guaranteeing accurate shadow rendering. Additionally, we perform data augmentation through various lighting settings. Here we show some examples of synthetic data. In all-modal completion stage, given an input image and visible mask, we first obtain the image latent through VAE, and it will serve as the initial frame of the video latent. Subsequently, the downsampled mask is concatenated with video latent fed into the video diffusion model. During generation, the input image features are extracted via clip and injected into the generation process. Finally, the last frame of generated video is the complete image. To preserve spatial layout information during instance regeneration, we propose a spatial alignment mechanism with shape prior injection. Specifically, we first recover the initial geometric structure from multi-view images and camera pose information using multi-view LRM. Then obtaining explicit geometric voxel through geometry voxelization, and extract implicit low-resolution voxel features via a structure encoder. These voxel features are then generate sparse structure through a structure generation model and decoder, ultimately recovering the complete 3D representation via a structure latent feature generation model. Here we show some interactive 3D scenes generated by HiScene and their editing results. Thank you for watching.